Alright, thanks for watching, and today I want to use the Intermediate Value Theorem to define the concept of a square root. More precisely, I want to show the following. Suppose here you have the parabola y equals x squared. Then, given y, so if I give you a y, there is some x such that x squared equals y. So fact, given y greater or equal to 0, there is a unique, it's the monique of the number world. So there's a unique x, non-negative, with y equals x squared. And this x, we'll call this square root of y. Okay? So now let's show this, and as I said, very quick application of the Intermediate Value Theorem. So proof. Alright, so fix y and let f be the function x squared. So let f of x be x squared. So what do we have? This is our parabola, f. And moreover, notice, well, f is continuous, and f of 0 equals 0. So it's continuous, and its initial value, it's 0, and here we're given y. Okay, non-negative. Notice, it's enough to find some value of f that is bigger than y, because then we can just apply the Intermediate Value Theorem. So just a little fact, there is a b such that f of b is greater or equal to y. So claim there is b non-negative with f of b is greater or equal to y, and then we would be done, because then by the IVT, then since y is between f of 0 and f of b, by IVT, we must find some x such that f of x equals y. Because again, IVT says f attains all the values between 0 and f of b, in particular y. So by IVT, there is x in, let's say, 0b, in particular non-negative, such that f of x equals y. In other words, x squared equals y, which is precisely what we want. All right, so let's now just prove the claim, and then we're done. And in fact, the claim is very quick to prove as well. So proof of claim. Well, suppose first of all that y is less than or equal to 1. Then we have a situation like follows. This is our parabola, and then this is 1, and this is our y. Well, in that case, just let b be 1. Because then b squared is 1, which is greater than y. So let b be 1. Then Facebook, so f of b, that's b squared, which is 1 squared, and that's 1, and by assumption 1 is greater or equal to y. So we have that, and then while in the other case, it's similar. Case 2, well, if y is greater or equal to 1, then notice the following. So this is 1, this is y, and well, the square of a number greater or equal to 1 is bigger than itself. Like 2 squared is greater or equal to 2, so in particular, let b be y. Because the point is, y squared is then bigger than y. Then f of b, that's again b squared, which here is y squared, and that's greater or equal to y. And that's also what we wanted. Last but not least, so we're done with the existence part. Now let's just show that there's a unique y that works. And for this, suppose, so uniqueness, so suppose we have two numbers, a and b, such that a squared equals y and b squared equals y. Well, then there are three cases. Well, either a is less than b, or a is greater than b, or what we want, a equals b. But here's the thing, if a and b, they're non-negative, then a squared is less than b squared, but then a squared is y, and b squared is y, and we get y is less than y. So that case does not work, and similar, this case does not work, therefore we need to have a equals b, and our uniqueness part is proven as well. All right, thank you very much.